All right, so we're, what is this, our fourth lecture in vapor power cycles. We've talked about the Carnot, we've learned, and this is one thing to walk away from this class that you'll remember for a long time. If you increase the boiler pressure on a vapor power cycle, it'll be better for performance. You'll be able to get a higher thermal efficiency. If you decrease the condenser pressure, worth repeating again and again, it's good for performance. If you superheat, it's good for performance. And last time we talked about reheating, meaning getting more heat back into that steam, having 2 turbine stages or 3 turbine stages, but reheating that steam, bringing more heat into the working fluid at high temperature, good for performance. Today, we talk about regeneration. I didn't make that word up. It's one of those confusing terms. What do you mean, regeneration? Well, all it is you have water, it's feeding the boiler. So we call that feed water. Why do we call it feed water? It's water feeding the boiler. It's going into the boiler. And that water that's going into the boiler can be pretty cold. And what we want to do is we want to heat it up before it gets into the boiler. Because once it's in the boiler, you're using that valuable heat source, think about burning coal, to heat up that water, to turn it into steam. So anything that you can use before you get into the boiler is helping you alleviate and reduce the primary heat source from the fuel that you're using, typically like coal or natural gas. Nobody burns natural gas. They used to, but nobody really does now burn natural gas to boil water to make power. You put it through a gas turbine. Gas turbines have come a long way. But anyway, so think about just boiling burning coal to boil water, or in a nuclear power plant, the fissioning process releases the heat to boil water. All right. So this is the regeneration or the regenerative vapor power cycle we want to talk about today. All right. So as review, we had this cycle last time where we go back for reheat between the first and the second turbine stages. And we looked at it and said, you know, that's helping us get some more energy into the working fluid at high temperature. That's good for performance. But then we still saw that state 6 was very cold coming out of the pump. If we had 8 megapascal is the boiler pressure, then it basically is changing phase at around 295 degrees C. True? And if we superheated it to 440 coming out, these are the numbers we worked at last time, then we pass it through a turbine. We stopped at 1 megapascal. So at 1 megapascal, we then reheated back up to 440. We then pass it through another turbine. Now it's way down to 20 kilopascal. These are just some numbers to give you a sense of the values. And then we put it through a pump that's back up right here to 8 megapascal, but the temperature was way down, like 60 degrees C. And now you can think about that cold water entering into the steam, and it's got to come out superheated vapor at 440. Well, first, it has to get up to the boiling point at the pressure of 8 megapascal. It has to get up to 295. So from 60 to 295 saturated liquid, that's a lot of heat addition. That's what we want to attack. That's what we want to affect. Because 295 to 295 saturated liquid to saturated vapor, well, that's just the job of the boiler, the steam generator. And then superheating it, well, that's just getting it in, getting that heat into the working fluid. But this is the area for improvement. Just as a reminder, what do you do? What's the strategy when analyzing a difficult problem like this? Make a table of all of the states and get all the properties. And it's a lot of work. We did that last time. Once you have all the, especially the enthalpies, that's the key column here, you can do energy balances around each of those components to get all of the heat transfers and work transfers. Notice that I busted up in that boiler into 3 phases. This is cooling the liquid from 60 to 295. That's a lot of heat. This is taking the liquid from state 7 to state 8, and that's boiling it. That's a lot of heat, but that's where we want it, changing the phase. making it vapor. And then this is superheating, so the total is around 3,000 kilojoules per kilogram, of which 35% is what we're going to attack. We're going to try and reduce that 35%. We're going to try and reduce from 1057 kilojoules per kilogram. We're trying to reduce that by doing some regeneration, preheating the feed water before it gets into the boiler. And that's going to be great for performance. All right, once you get all of these, you calculate the backwork ratio. So this was a review, and how are we going to improve this cycle? We're going to try and reduce the amount of heat. We're trying to bring up the temperature of that feed water before it gets into the cycle. So here is our existing cycle. We have the reheat, 2 turbines. What did I cover up in the box with the black right in this region? What I don't want you to see. But the goal of what I don't want you to see, don't lose sight of what the goal is to take 60 degrees C and get it as close as possible to 295 degrees C. Can you get it 295? Well, you'd be a very clever engineer if you could. But we're going to get it closer and closer. How would you do it? Well, we would use a feed water heater, and we have 2 types, open and closed. Let's first discuss the open. We studied open heat exchangers in chapter 4 or 5, somewhere back there. I think it was 4. And then we analyzed also the entropy in chapter 6. These are your old friends. Do you recognize your old friend, the old heat exchanger? 2 inputs. 2 inputs. How many output for an open? 1. And we can do a mass balance and we can do an energy balance. So what you're doing is you're taking some of the steam that comes out of the first turbine and you're diverting it down to mix, to bring up the temperature right here. That's what you're trying to do. Well, if you're taking some out of that stream, then less of it continues on to go to reheat. It used to be 100% went back over to reheat. But now you're not sending 100% over to reheat, are you? So they're going to have an additional complication that we have to deal with. So this is the idea. Okay? Now look at how many pumps do you have now? 2 pumps. What do you like to feed a pump? Saturated liquid. The optimal design for this open feed water heater, what do you think you're going to feed it at state 7? Don't forget that. So students be like, I don't know how to solve this problem. Well, what do you want to put into a pump? Saturated liquid. That actually tells you how much you divert. Here, that's the bottom line. It gives you how much you need to divert so that you get 7 exactly where you want it. You want state 7 to be saturated liquid. So that's the question. How much steam do you need to divert? To answer that question, I have to do a pretty good job of understanding my mass flow rates. This is easy. This is easy, but I need to go slow because it can be tricky if you're brand new to it, right? So what we do is we come out of the steam generator right here, the primary pass through the steam generator, not the reheat pass, and we go into the turbine, the first turbine. And you have to make a name for this. Maybe I call it M.1. I don't really like it because it's really not at a state. It's in a pipe connecting 2 states or connecting 2 components. It's going out of the steam generator and into turbine 1. So maybe we'll call that into turbine 1. Does that syntax make sense? This is the mass flow rate into turbine 1, M dot subscript T1. All right? If we use that subscript, this is M dot T2. What would that be? Mass flow rate into the second turbine. That would be this flow rate going into the second turbine. Can you just tell me which one? Are they the same? Is one larger than the other? This is going to be easy if you got that down. You see that? Why is it larger? Because some was diverted. What syntax do you want to use for the mass flow rate that's diverted down to feed the open feed water heater? I'll just make one up. Down to feed the open feed water heater. It's kind of like what went into the feed water heater by being diverted. Okay? I know there's no perfect because this is also into the feed water heater, but let's do this. Let's track out this. If this is m dot T1 that goes into the first turbine, it's coming out of the first turbine. And then what happens is some of it, m dot open feed water heater, gets diverted downward. So what continues to reheat, and that way it's going to be what came out of the first turbine minus what was diverted to feed the open feed water heater. Do you see that? It's subtraction there. And then how about right through the second turbine and coming out of the second turbine? The same. How about through the condenser and out of the condenser? The same. So this is all m dot T1 minus m dot open feed water heater. And then through the first pump, the same. Let me ask this. The mass flow rate that goes into pump 1, compare it to the mass flow rate that goes into pump 2. It's less. Mass flow rate into pump 2 is greater than the mass flow rate into pump 1. Why? We joined back up those two fluid streams in the open feed water heater. And now that's what goes into, is what goes into the second pump. Is that what goes into the first turbine? Yeah, you're absolutely right. Well, so we track now all of the mass flow rates through the system. And what we do is we come down here and we do a little control volume analysis around the open feed water heater so that we can calculate how much steam is needed to be diverted to feed the open feed water heater. All right, so let's do this. Let's write a mass balance. It's real easy. We have this problem with syntax, though, or the subscripts. We have the mass flow rate that feed the open feed water heater, that's what's diverted, plus the mass flow rate that goes through pump 1 is equal to the mass flow rate that's going into pump 2. That makes sense? And then, hold it, we can substitute this. That wasn't that the mass flow rate that went through the first turbine minus the mass flow rate of the open feed water heater? Sure enough, that sure is. And then what is this? Mass flow rate pump 2. Isn't that what goes through the first turbine? So if I want, I can rewrite this and I'll write it. The mass flow rate open feed water heater plus the mass flow rate T1 minus the mass flow rate open feed water heater equal to mass flow rate T1. It's a trivial statement. I mean, you could do this. That cancels that. This cancels that. You don't have any equation. I know. But if we divide the whole equation by mass flow rate that goes into the first turbine, what I finally pick up, I don't like my math there, m dot T1, m dot T1, m dot T1, is you run up with almost similar statement of triviality, but you get the mass fraction. That's what the textbook uses, the symbol Y. For the mass fraction that's diverted to feed the open feed water heater. So they'll put a little Y right there. And they'll say Y is 20%. What's that mean? That means 20% of what came out of the first turbine goes down. 80% continues in the loop. So Y plus, and then this is 1 minus Y, is equal to 100%. There's not much in the mass balance except for I need the definition of Y, which is what is diverted to feed the open feed water heater of what comes out of the first turbine or when it went into the first turbine stage. All right. Now that we've done the mass balance, and you're pretty good at that, do an energy balance. Professor, I need my equation sheet. Nope, no equation sheet needed. I want you, I'm going to pause, I'm going to walk around this room. Professor, is this a transient problem or a steady state problem? Professor, is there a shaft work in or out of this control volume? Professor, is there heat transfer in or out of this control volume, with the surroundings? Can I neglect changes in kinetic and potential energy, Professor? Write the first law. of thermodynamics applied to this device. I'll come around and see how many people get there, because that gives you the equation for Y, which is the mass fraction that's diverted. So the energy balance equation really boils down to one in plus another in equals the out. And you're going to get the energy balance equation will be something like the mass flow rate. Now the challenges with the subscripts. I know that some people write mass flow rate 6 and mass flow rate 2 and mass flow rate 7, indicating the mass flow rate from 6, coming into the feed water heater, and then from 2. The only challenge is M.2 really is like, M.2, is that what comes out of the turbine at state 2? Or is that what's diverted or what goes up? And so I spent a little time on trying to avoid the number 2 because it's a little confusing right there. But it makes sense for 6, it's what goes through the pump, And it makes sense for 7, what goes through this pump. And maybe I just changed that subscript so it makes more sense. It says what goes out of pump 2 or through pump 2, what comes out of pump 1, and then what comes down to feed the open feed water heater, right? So those are my 3 mass flow rates. This is the mass balance by, This is the mass balance by itself, but if I multiply by the enthalpy at state 6, and the enthalpy at state 2, and the enthalpy at state 7. Is that it? Is that what we had? I got an error?
No, you haven't taken it all away.
This is P2 going through pump 2.
That's right.
And this is 7. Oh, you want me to continue the manipulation?
Oh, yeah.
All right, no problem. So what we do is we divide this equation by the mass flow rate that basically goes through pump 2, which is the same as the mass flow rate that goes into the first turbine stage, which is the same M dot right there, right? So if we do that, we got M dot T1, M dot T1, M dot T1. Okay, now we stare at this for a minute. What is this ratio? It's what goes through the first pump divided by M dot T1. 1 minus Y. That is a very clever individual that made that observation. Isn't it 1 minus Y? It is 1 minus Y times H6 plus, what is this ratio? Y times H2 plus, what's this ratio? Whoops, that's not a plus, that's an equal sign. 1 times H7. Now, do you like that one? That's where you were, right? The first time you see that equation in the book and they say, oh, just the mass balance, energy balance, and you'll get it. Well, you got to work to get it, right? But there it is. And so the equation for Y, rearranging, is going to be the H7 minus the H6 divided by, I'm just doing the algebra in my head here, the H2 minus the H6. That's the equation for the fraction that needs to be diverted. Yes?
This is all really useful when the mass flow rate isn't given, right?
Yeah, we don't...
Mass flow rate, we wouldn't need this.
No, let me back up a little bit. We need this all the time. It basically tells us the fractions that diverted. The key thing is that you need to know that H7 really is predetermined. I want that Y, that fraction, to be diverted such that H7 is the saturated liquid's enthalpy exiting the open feed water heater. That really is the key, I think. People have to understand, I really want this to be a particular value. And Y is determined such that it is that value. What is H7? H7 is H of F at that high pressure coming out of the feed water heater. Let's talk about pressures. How many unique pressures? Here's my 3 fingers up in the air. I gave away the answer. How many unique pressures are there in this system? 3. And if you run with my pressure of 8 megapascal, which is, I think, easy to talk through, and 20 kilopascal, then there's another intermediate pressure. That's that pressure between turbine 1 and turbine 2. And remember last time I asked that trick question, it's not trick, but it makes students think, and I find that sometimes students will answer incorrectly, is the pressure at state 2 the same as the pressure at state 3? Yes, and a lot of students will say, no, there's a reheat in between, so it must be different pressure. But the reheat's just a heat exchanger, they're the same pressure. Turbines change pressure, pumps change pressure. Boilers, condensers, reheats, heat exchangers do not change pressure. With that, armed with that, what's the difference between the pressure of state 2 feeding this open feed water heater, state 6 feeding this open feed water heater, and state 7 coming out of the feed water heater? P2, P6, and P7, which one is the greatest? What has the highest pressure? And which one has the lowest pressure? No, they're all the same pressure, aren't they? Isn't P2, P6, and P7 the same pressure? How do you know that, Professor?
Because the heater can't change pressure.
The heat exchangers, go back to chapter 4. What's the purpose of the heat exchanger? What does it do? It doesn't change pressure. If it does, if you have a real heat exchanger, there will be some pressure loss because you're forcing fluid through tubes or over tubes or something. But we're neglecting that. We're saying it's a small negligible pressure drop in the direction of flow. And so the pressures are the same. So when you solve these problems, march through and pick out which two pressures are the high pressure. The two pressures, the high pressure, 1 and 8. What two pressures are the low pressure? 4 and 5. What about 6, 7, 8, and 3? Did I get it right? 6, 7, 2, and 3. 6, 7, 2, and 3. All the intermediate pressures. Whatever intermediate pressure that you picked. I think we picked 1 megapascal, or maybe 2. Something like that. Yeah, let's go back, look at our numbers. Which value? Come on now, let go. I picked 1 megapascal for that intermediate pressure. There's confusing wording as soon as you start splitting the flow. With reheat, did we split the flow? Not really, right? But now with regeneration and we have feed water heaters, some flow goes to feed the feed water heater. We're splitting the flow. So you'll get a word, this is directly out of the textbook, you'll get confusing wording for like, make this calculation. They say, determine the heat transfer from the working fluid passing through the condenser to the cooling water in kilojoules per kilogram of steam entering the first turbine stage. Hey, first turbine stage, I thought you were asking me about the cooling water in the condenser. You have to slow down and read a sentence like this 4, 5 times to understand what's going on. First of all, you have what we call the working fluid going through the condenser. That's this working fluid phrase. If we can have a refrigerant run a vapor power cycle. Yes, you can. But primarily our working fluid is water, steam. We boil it and condense it. But then we also have cooling water going in and out of this condenser. What's that? You may have a lake, and that's actually where the heat is being rejected to in the heat exchanger called the condenser. So the lake water is the cooling water, and it comes in maybe, 20 degrees C and goes out 30 degrees C. See? The cooling water is not the same as the working fluid. That's the first big distinction. The second is you're asked to find the heat transfer. So you're thinking, okay, I can do that. It's going to be you're going to either ask me to calculate Q dot or Q dot per M dot, right? Q dot per M dot. That's our heat transfer. I continue to read the problem and I even see, oh, look it. They're asking me to calculate it in kilojoules per kilogram. Are they asking me to calculate Q dot or Q dot per M dot? Q dot per M dot. Everything looks great. I've analyzed these heat exchangers before. I know this is a lowercase q. I use that. And when I do the first law analysis around this, focusing on the working fluid, I know that it comes in higher enthalpy, H4, goes out lower enthalpy, H5. That's the first law of thermodynamics. It looks great. Except for of steam entering the first turbine stage. What? Of steam entering the first turbine stage. What does that phrase mean?
M dot is in the one.
It's a particular m dot. Is it the m dot that's going through the condenser? Nope. It's the mass flow rate that's entering the first turbine stage. This is super confusing, but you'll make sense of it. You'll get it because it's very convenient to make the calculation this way. So you say, hold it. If I'm looking for this Q, lowercase q of the condenser, it's really m dot, q dot divided by m dot going through the condenser, but I don't want it through the condenser. I want it through the first turbine stage. We'll just do this. Multiply. I'll cancel these two. Voila. Is that right or wrong mathematically? Won't it be q dot in the condenser per mass flow rate going through or entering the first turbine stage? And then I say, oh, you know what? If I just focused on the heat exchanger, I already know what that is. That's H4 minus H5. And then what is this term? 1 minus y. So there you go. So does that make sense? That's what I would be asked to solve for. So I'd calculate the enthalpies at 4 and 5, get the difference. I'd calculate the mass fraction that's diverted to the open feed water heater, y, and there I'd make the calculation. We just have to jump in and solve a problem. All right. Water is a working fluid in a regenerative vapor power cycle. What does the word regenerative mean? I've got a feed water heater. Only one that, well, we've looked at only the open feed water heater, but we'll look at the closed in a minute. So we have the 8 megapascal, 440 degrees C. That's what goes into the first turbine. It exits at 1 megapascal. So that's our intermediate pressure. 8 megapascal is high, 1 megapascal is intermediate. And then it goes to condenser 20 kilopascal. So our pressures really have not changed. I'm trying to keep them consistent as we work different problems. But here we have some of the steam after the first turbine is extracted to feed an open feed water heater, while the rest of the steam is reheated up to 440 and then enters the second turbine stage. So make the calculations, get the backwork ratio of the cycle and the thermal efficiency. How do we do this? Well, make a sketch of each of the components. I mean, can you get, a lot of you already got it, turbine 1, turbine 2, right? You got steam generator, comes out, goes here, comes out, oops, I need to divert some, goes back for reheat, goes over to second turbine stage, after that goes to the condenser. This is too much to memorize, Professor. No, you should be able to do it for the exam, given a word problem like this, make a sketch of the schematic, of the layout of the power plant, as well as sketch it on a TS diagram. Am I helping you for the exam? Am I? I hope I am. Telling you, hey, don't be surprised. Professor, I'd like a schematic of this. No, you've got to generate it from the words. And then after the condenser, you got to come out here with a pump. After the pump, you're going to go into an OFWH, too many acronyms, sorry, open feed water heater. And then after the feed water heater, you have to boost it to another pump to feed the steam generator. And sometimes I like to draw a line like this, indicating that's going to be heated between the input and output, the primary input and output of the steam, not to be confused with the reheat. Sometimes students will calculate this Q added there nicely they'll forget this Q in the energy balance, the Q from the reheat. All right, so now we have to throw numbers for our states. Start 1, start 2, then 3. Or should I put 3 before the reheat and then... No, this is correct, right? After the reheat is 3, then 4, then 5, then 6, then 7. Do I need an 8? Yes. Make a table of the properties. Get the pressure straight. There's only 3 pressure values in the whole system, right? Okay, we just did it. Put them in the table. Then think about how I'm going to be determining state 1. Oh, I think it's pressure and temperature fix the state. Hey, I can get enthalpy. That's the most important. How about for state 2? What is really going to get state 2? Pressure and entropy. That's right. We specify it drops pressure and it's isentropic expansion from 1.
If it doesn't say ideal Rankine, like I still assume isentropic.
If you have no information given, then you assume it's isentropic expansion through your turbine, just the same for the pump. But if you were given an isentropic efficiency, then I would do this. I would introduce state 2S and 2 actual, and I would help the table organize the workflow to make that calculation, because when you're given an isentropic efficiency of a turbine, it's typically a 2-step process. So introduce additional state in the table. It'll help you and avoid an error. And then you go 3 to reheat, and then you go 4S and 4 actual if you had efficiency for the turbine. Otherwise, just call it 4 and it's isentropic expansion. And then 5, and what's coming out here? Sat liquid. You feed that into the pump, and it comes out. The enthalpy at 6, if you've solved these problems already, it's the enthalpy at 5 plus VDP. VDP, that's the best way to calculate the work, isentropic work required to run that pump, and the best way to get the enthalpy at state 5. All right? Okay. Likewise, H7, well, that's saturated liquid at that high pressure. And because you know the pressure, you can get that enthalpy. Once you come through here, you want to eventually calculate the Y. Usually I set and calculate the Y on a separate line. But I need to know the enthalpy at 2. I need to know the enthalpy at 6. I need to know the enthalpy at 7 before I can get the mass fraction. True? All right. Once I have a table of all the properties, what is my next table of? All the components. I want the Q's and the W's for all the components. If you're brand new to this game, I would make a Q and a Q star and a W and a W star columns. I'd make 4 columns in my table for each component. Let's say for turbine 1, let's say for the reheat, let's say for turbine 2, let's say for the condenser, let's say for pump 1, and I'm going to stop there because I know that I can explain why I have 4 columns. Why do I put a star on one, an asterisk, or something like that? Well, this would be my normal Q, which is per unit kilogram of what's going through the device. And then this one would be per kilogram through the first turbine. Normalize everything to the first turbine. See? Because when you then sum the Q's for the cycle, if you sum this column, it ain't going to work. But if you sum the Q star column and you sum the W star column, it will work. It will work. Okay? Because you got everything on the same per unit kilogram basis. All right. So, maybe, should I flush one of these out or not? How much time do I got? Oh, nope, I don't have enough time. I have no time at all. But, okay, I'll pick it up next time. Thank you for your attention.